Okay. So let's get started. Today the topic is going to be quantum probability, which is a generalization of normal probability. So let me recap a bunch of stuff that we did last time concerning mixed states, which is the sort of most general kind of state in quantum computation. If you have a mixed d-dimensional state, it's kind of like, you have various probabilities, pi, of different, we'll call them now pure states. These are the d-dimensional complex vectors, unit vectors. And whenever you have such a mixed state, there's an extremely elegant and complete way to encode it by a matrix called the density matrix, usually denoted rho, the d by d matrix. And you get it, well, like this. So a pure state psi I corresponds to this d by d matrix, which is like a column vector times a row vector. And you add those all up with these coefficients p1 through pm, and that's the matrix rho. And as we saw, like this matrix rho actually encodes, or it's contains all the information you need to know in order to understand like every possible measurement of this probability distribution on states. And therefore, we just take it as defining the quantum state. Right. So these matrices, the density matrices, have various properties. First of all, the Hermitian, which is like the complex analog of symmetric. And so if you have like a Hermitian matrix, it's a density matrix. It's of this form if and only if two conditions hold. First of all, it's quote unquote positive as a matrix, or positive semi-definite, which means that well, if you look at this u rho u, this is rho vector times the matrix rho times the column vector u. This is always non-negative. And its trace, which is the sum of the diagonal entries, should be 1. Okay, so any matrix like that is a density matrix that has some corresponding mixed state and vice versa. And another thing that I want you to remember is this important fact about Hermitian matrices. They're our favorite kind of matrix. They're such great matrices. Whenever you have a Hermitian matrix M, you should really think of it as just coming with some orthonormal basis of d-dimensional space and some real numbers, lambda 1 through lambda d, associated with the directions. And then the action of M on that space is to like stretch by factor lambda I in the direction of the ith basis vector vi. Okay, so it's some sort of just generalized stretching thing. Once you pick the right basis, there's no shearing or anything. And these lambda i's, which are always real, are the eigenvalues, and the vi's are the eigenvectors. And we argued last time it's not hard to see that once you have any old Hermitian matrix, this condition of it being like a positive matrix, a positive semi-definite matrix, is equivalent to all these eigenvectors being positive or non-negative. So all these stretches are non-reflections, or positive stretches. And this condition that the trace is 1 is actually equivalent to these eigenvalues adding up to 1. And therefore, whenever you have a density matrix, these eigenvalues are non-negative numbers adding up to 1. So you can think of them as forming a probability distribution, or in fact a probability distribution on the eigenvectors. And therefore, you'll always, for any density matrix, you'll have kind of like a nice mixed state, one where they're like d. It's a mix of d things, where d is the dimension. And these d pure states that it's a mix of are orthonormal. OK, any questions about this? All right. Let me remind you a little bit more about this. So now that these mixed states, which I'm going to just sort of identify with density matrices, I'm not going to make a big difference between this kind of probabilistic viewpoint and just the matrix viewpoint. Now that these are like our basic notion of a state, we should think about all the things we like to do with quantum states and how they work in this density matrix setup. So let's see, what are the actions here? One thing we like to do is apply a unitary transformation. And when we just had the old unit state vectors, pure states, we just multiplied by u. But now it's a bit different. The way that works with density matrices is that rho gets mapped to this u rho u dagger. OK. Another thing we like to do is measure states. And in particular, you can measure in any orthonormal basis, as we know. And one thing that we saw last time is if you measure in a basis, an orthonormal basis, let's say U1 through UD, then you get, your measuring device gets the outcome or readout I with probability something that looks like that thing that shows on the definition of positivity, UI bra times rho times UI. In particular, if you're measuring in the standard basis, then these different numbers are the diagonal entries of rho. And so in particular, you can see that this will add up to 1, and so that sort of makes sense. Now, of course, also when you measure a quantum state, it changes the state, right? It collapses. But I'm not going to write here what the quantum state collapses to. You could. But at least in today's lecture, we'll kind of, again, take this philosophy that like once you measure a quantum state, you're kind of done with it. Like you won't like use it again. Okay. So that'll just save me a little time. And one more thing that we can't remember if we mentioned last time, but one more action that you sometimes do with pure states, we talked about it in, I don't know, lecture 3 or 4 or 5 or something, is you just have two pure states, or you have two quantum states that were prepared separately, and you just decide to like, consider them jointly as one big state. So let me tell you the story now with density matrices. I'll call this, I don't know, adjoining two states. So let's say if rho is the density matrix for a mixed d-dimensional state. So you have some quantum particle with d levels or d basic states. It has a mix density matrix rho. And let's say sigma is the density matrix for some e-dimensional state. And then we know that when you just consider these two particles as one joint system, it's d times e dimensional. The whole system is d times e dimensional. And if this is got various probabilities pi of psi I, and this has got various probabilities qi of phi I, we assume they're created separately, so you have kind of like a product probability distribution on pairs of pure states. And let me just say, if you do the math, so I'll call this an exercise, or it'll be on the homework, which will come out this afternoon. Its density matrix is the one thing that you would guess. Rho Kronecker product sigma. Okay, so that's actually the same rule that it is when these are pure states. And now it's you can work out quite easily. It's the same rule again for matrices. Okay. So today we're going to talk about the probability of mixed quantum states. And I'll get into that but just a second. But this is a very math heavy lecture, and we have to have one more little math interlude before we get there. So bear with me while we take a little linear algebra interlude. It's actually concerning this quantity I just erased, the trace. So here's a little proposition. Let's let A be a matrix, and B be a matrix, and then, okay, we're going to look at A times B. I set up the dimensions so that that's legal. And then we're going to look at the trace of this. Trace is the sum of the diagonal entries. Well, it's equal to the trace the other way. Okay, of course, for matrices that A times B does not equal B times A in general, but the traces are always the same. And I must say, for the most part in quantum probability, you'll see trace floating around all the time. And I almost think the best way to think of it is like a calculational trick. It's just like a quantity that comes up, and you learn to play manipulation games with it. Less so does it have a real meaning. I mean, its main meaning is the sum of the eigenvalues. But there'll be a lot of calculational tricks involving it. So here's trick number 1. OK, I'll tell you the proof of this. You just write it out, and it works. So trace of A times B, by definition, is the sum of the diagonal entries. So I goes from 1 to D, oops, AB times I. Now, you have to remember the formula for the entry of a product of two matrices. And you'll remember it as I write it out for you here. It's sum I goes from 1 to D of, you put in all indices j that can go in the middle, and, well, you'll see. It's sum j equals 1 to d prime, a ij times b j I. I personally like to think of this sometimes like, if it's like the adjacency matrix of a graph, right? Then the square is like the adjacency matrix of the length 2 path graph. And so you have like a path of length 2 from I to j and then j to I. Well, anyway, that's how you can think of it. OK, now in life, of course, whenever you see two sums, your first instinct should always be to interchange them. So let's do that. And we get sum j goes from 1 to d prime. Sum I goes from 1 to d. And this is multiplying two numbers, so let's just interchange them too. bji times a ij. And now you may again recognize this is the entry of a certain entry of the matrix B times A. We've got a little length 2 path here. This is sum j goes from 1 to d prime of the jth entry of B times A, OK, which is trace BA. OK, so I felt obliged to show you that because it's a fact that used all the time in quantum information theory, quantum probability, which is what we'll be talking about for the next few lectures. And in particular, once you have this, you can do this like kind of almost comical trick that will come up again a lot. It's considering this quantity here. So this is a number. This is like a row vector times a square matrix times a column vector. So it's a number. Of course, if you're just we're acting like a robot, you'd be like, well, actually, technically, it's a 1-by-1 matrix. OK? That's true. So it is a 1-by-1 matrix, and therefore, it's the same as the sum of its diagonal entries. It's only one entry, and it's diagonal. So this is the same as the trace of ui times rho times ui. And then you're like, aha, I'm going to apply this proposition with this matrix here. It's a row matrix, but anyway, it's a matrix, being A. And this matrix here being B. OK? And then, then I'll swap them. So I'll get trace of, I put B first. That's rho times the column vector u. And then I'll put A, which is this row vector I. OK? And this is funny. It looks like you've made terrible progress here. You've just taken a simple thing, just like a number, and now made it more complicated. But it's going to be good to have it in this formula. And it is more complicated, right? This is a square matrix. It's d by d. This is also a square matrix. It's d by d. And so you're multiplying two square matrices and then summing the diagonal to get all the way back to this number. But it's going to be good to have this little fact in our hands. And let me just remind you, one reason it's good is this matrix has a meaning. You studied this in homework 2 or something. This is a matrix, so it's a linear transformation. And what transformation is it? It's the matrix that acts by projecting every matrix onto the direction or the line through ui. OK, so this is for whatever reason, the greatest trick that you just apply over and over and over again in quantum information theory. And right, let me tell you yet another trick based on this fact. Also, suppose I just looked at exactly this quantity, but for math reasons, I put a dagger on the first guy. So I looked at trace of A dagger B. Well, I can use these self-same formulas. And we'll get that this is the sum. I guess I'll just use this formula right here over I and j of A dagger's ijth entry times B's ijth entry. Okay, and dagger is basically transpose, right, which exchanges rows and columns. There's also the complex conjugation business, which is a little annoying. But let's just do that here. So we get sum over ij of A ji. That's the transpose thing. Okay, fine. I put a star in there for complex conjugate 2. Times B. This one should be ji. Thank you. Something terrible was happening. Okay, good. Ji. Good. And now, I mean, it's a little funny that, let me just, this sum over ij, let me just say it's sum over ji. It's the same thing. And now, like, the indices are matching up. So we're actually here, we're going through all the entries in these two square matrices and multiplying, like, the matching entries. Okay, there's a complex conjugate too. So actually, this is exactly like the dot product of the matrices A and B. If you're just like, hey, these numbers in my matrix are arranged in a square, but whatever, I'll just do a dot product between them. Right, so this is like the dot product of A and B when they're just viewed as boxes of numbers. And we even have like the complex conjugate in there that you're supposed to do when there's complex numbers involved. And so let's just use this somewhat standard, somewhat not fully standard notation. I'll just call this quantity A, angle brackets B for this. Okay, because it's an inner product between, I don't know, matrices. Okay, well, I like to write it like this. It reminds me of the normal vector dot product or inner product. Okay, so I'm going to use this notation a lot. Angle brackets of A comma B is just this dot product of two matrices. And it also has this trace formulation as well.
What's the conjugation?
Yes. I should have mentioned that basically, don't worry too much about this complex conjugation because most of the time we'll be applying these little facts when A, and also B, but even just A, is a Hermitian matrix, which means that A dagger is the same as A. So you're just like, great, I don't have to worry about this dagger. Okay, so I needed to do that. But now we're ready to talk about somewhat more interesting things, quantum probability. So you all took at some point in your life, hopefully, probability 101 as sophomores or whatever, and you learned all the basic things. And that's the rules that govern real life flipping of coins and rolling of dice. And today it's going to be like quantum probability 101. And well, first of all, this is a strict generalization of classical probability. And so, it governs the flipping coins and the rolling dice, but also, the behavior of quantum particles. Great. And just to motivate it, we're always going to be comparing it with the rules of classical probability. So what is in classical probability, literally definition 1? It's the first day of your discrete probability class. They're sample space and probabilities, right? So they might say something like this, a D outcome. Okay, they probably wouldn't put it quite like this, but it's basically, a D outcome probability distribution, or a probability distribution where the sample space is the numbers 1 through D, or a D-sided die, is, well, it's basically a bunch of numbers that add up to 1. Let's write it like this. Vector P of length D with two properties. P greater than or equal to 0. Here I mean element-wise, so all the entries are bigger than 0. And, the sum of the p's is 1. Okay? It just says this forms a probability distribution. Okay. Well, in quantum probability, we have a very, very similar looking definition 1. And we saw it already, but I'll write it again. This is in quantum probability. A d-dimensional state or density matrix okay, is a Hermitian matrix rho, you just draw P and put a little curve at the end with two properties. They look almost the same. Rho greater than or equal to 0. Remember, that's a matrix thing. It means it's positive semi-definite. And this other condition, this normalization condition, the trace is 1. So you see they look very similar. And you should really, in particular for today, think of like rho as like a quantum source of randomness, like a quantum die. Like it creates randomness in this world. And in fact, you can get quantum probability just by like taking the laws of classical probability, and everywhere you're going to say vector, say Hermitian matrix instead. That's basically it. Okay, that's a little bit fuzzy, but the reverse direction is like literally true. You can take the laws of quantum probability, which we'll see, which is all about like Hermitian matrices. And if every matrix you encounter is a diagonal matrix, then it's exactly classical normal probability. So that's the sense that it reached, this quantum probability, which we'll start to study, truly generalizes good old normal probability. Okay, so I'm really going to start to explore this analogy. Maybe a good way to think about it is like, in classical probability, and like maybe somebody hands you a d-sided die and you don't know much about it and you want to start to study it with the laws of classical probability. Similarly, yeah, maybe you have some quantum machine or experiment which generates a particle which you can then try to measure or learn something about. And so it's like sort of an unknown source of quantum randomness. Okay, so let's pursue this analogy a little bit. So recall, as we said before, if state rho is measured in the orthonormal basis U1 through UD, then the probability that your measuring device reads out I is, well, first we wrote it like this. I mean, we computed this formula last lecture, and it got down to this number. And now I'll use this little business to notice that it's the same as trace rho times this matrix. And here, as I said, it's an example where like you can sort of stop worrying about this dagger. Rho, which is always going to be sitting here, or usually, is a Hermitian matrix because it's a state. So it's the same as rho dagger. And therefore, this is, with this just notation that we invented, this is rho matrix interproducted with the matrix EI, where EI is this matrix that is written here. This matrix that's like the project onto UI matrix. Yep.
So for the source of randomness, do you think about this as a machine that produces exactly the same particle every time? It's just we don't know what state that particle.
Yeah, if you're thinking about it in that way, which is the way I often am thinking about it. In general, like, you might just like, I don't know, find a particle on the street, or like you just have like one particle and you want to understand it. Yeah.
Specific particle. It's not like a
yeah. Yeah, so like, it's true. I mean, at the very end of this lecture, I'll talk a little bit about, learning problems and sampling problems. And like with a die, like a mystery die, you can roll it a bunch of times, and you get like sort of many draws from this distribution. Here, it's like, yeah, maybe you should imagine you have like some quantum apparatus that produces a particle in this mixed state rho, and that you can do it many times. Okay. And while I have this up here, let me make a couple of remarks. First of all, this matrix EI itself is a positive semi-definite matrix. That's a little exercise for you. You can think about why it's true based on this definition. Well, basically, this is a Hermitian matrix. So it has its own stretch factors and orthonormal basis. And basically, it has 100% stretch and stretch 1 in this direction and 0 elsewhere. So while it's eigenvalues are positive, or you can just see it directly from the definition. And also, this one's also a little bit funny, but E1 plus dot 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 plus ED is, well, yeah, this is the matrix whose operation is to project onto the ith direction, ui. And so if I add these all up, what operation does it have? It's the identity, yeah, because for any vector, you can write it in this basis. And then this sum of projections will just stretch it by factor 1 in each of the directions. So in other words, it'll just do nothing to it. So this is actually the identity matrix. Which is funny because it's true for any orthonormal basis, U1 through UD. But okay, that's something you got to get used to. By the way, I got on this in homework 2 too. I really like to write the identity matrix with as a 1 instead of an I. So I'll do it. Great. Okay. And now let me give the first example of comparing this to the classical world, or the classical probability. Okay, so let's say you're given a probability distribution P on the numbers 1 through D. And let little ei denote this vector, where this 1 is in the ith position. It's kind of like the indicator vector for the ith position. Then Pi, which is the probability when you make a draw from P that you get I, is, well, it's the inner product of these two vectors, P and EI. Right? This is the usual good old classic dot product. Which looks similar, right? And also, if you notice, well, EI, all these EI vectors are non-negative entry-wise. And if you do this, E1 plus dot 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 plus ED, well, you get the all ones vector, which I'll write as 1 vector. Hey, so isn't that beautiful? I mean, it's the same situation, kind of. Okay, so you can see actually this is, you can kind of recover this situation if rho is a diagonal matrix with P on the diagonal, and this is the standard basis. Okay, so that was like a little warm-up for what we're going to do today. And in general, what I'm going to do today is develop definition 2, 3, and 4 of quantum probability 101. So in particular, in classical probability, definition 1, sample space. Definition 2, you define events. Definition 3, you define random variables. Okay, I'm just going to define events and random variables in the quantum world, and we'll see these great analogies. Then I'll talk a little bit about what you can do with all this stuff at the end. Okay, so let's stick with classical probability 101, definition 2, which is about events. Once you define sample space, first thing you define after that is events, right? Okay, so this is actually a little bit tricky compared to random variables, which will be the third thing we do. And so I'm going to write some definitions about events that look a little bit weird. But you guys can handle it, because we're just talking about classical probability 101, right? So even though it's a little bit weird, you'll be able to deal, I hope. Of course, I'm writing this in a weird way so that it'll most naturally generalize to the quantum case. Okay, so let's say you're given a probability distribution P on D outcomes. I want to define some, let me just write an acronym so I don't have to spell it out. Mutually exclusive and collectively exhaustive events basically just a bunch of events where exactly one of the events always happens. Okay, they partition the sample space in some sense. And I'll call them event 1 through event m. And I'm just going to talk about like a few ways you could cook up such events. Mutually exclusive, exhaustive events where one always happens. So the naivest way is just exactly like this, which is the number of events is d, the same as the number of outcomes. And event I is just the event that like I is drawn from P. I mean, you can have that, right, where like, you have an event for each actual outcome. That's sort of the simplest thing, and that's sort of what we talked about a little bit over here. But you can actually have like these events with like m being less than d, or in a certain sense more than d, as we'll see. So another thing you can do is just so you have a name to hang on to it, I'll call it lumping, is you can like group some outcomes together and call like a group together bunch of outcomes like an event. This is like quite common, right? So for example, I'll give like almost the simplest example. Maybe you're like, okay, I'm going to define event 1 to be the event that the draw from P is an odd number. Okay, and then I want these events to be like mutually exclusive and exhaustive. So let me just say event 2 is that the draw from P is an even number. Okay, so now I have two events. They partition the sample space. Great. And I'm going to ask you to like identify these two events with their indicator vectors. Okay, we only have two events here. It's a pretty special case. You could have more. In this case, it'll be like little e1. This is like the indicator that the draw is odd. So it's that either 1, 3, 5, etc. is drawn. So this indicator looks like this. And the indicator for event 2 looks like this. Okay. And well, I want you to notice a couple things. One is, what's the probability of event 1 happening? That the draw is odd. Well, of course, it's just P1 plus P3 plus P5 dot dot dot. But notice that's, again, the inner product of P with E1. Right? The inner product of the vector of probabilities with this thing picks out the outcomes that correspond to the event. And of course, similarly, probability of event 2 is the inner product of P and E2. And again, I want you to notice these two facts, which is that in this situation is a bit special because I only did two events, but you could have had more. The EIs are non-negative. All their entries are non-negative. In fact, there's 0 and 1 in this case. And they sum the EIs. Let me write that. To the all ones vector. Okay, and they sum to the all ones vector because these events are mutually exclusive and exhaustive, right? One of these two events always happens, so you need that like for each coordinate, like if that is drawn from the distribution P, that exactly one of these guys happens. So far, so good? I know it's like slightly odd. Good. So this is like the way actually you normally think about events. You like lump some outcomes together and call that an event. Now, I also want to have like a version of events where actually you can have more than D, the number of outcomes, many events. And that doesn't seem possible at first, but it's going to be possible if you allow yourself to use additional randomness. Okay, so now the little classical probability 101 story is going to seem a little bit funny, but like this is the best way I could think to describe it. So hang in there. So suppose you want to sort of just take this as like the definition of mutually exclusive and exhaustive events. So suppose like E1 through EM are any, and now I'm going to put this in like giant scare quotes, indicator vectors satisfying that they're non-negative and they sum up to the all ones vector. And I put these in scare quotes because now I'm not going to insist that these are 0, 1. That they can have entries that are not, these should be in RD. They don't have entries that are necessarily 0 and 1. Okay, so of course they're going to be greater than 0 and adding up to 1, so they're going to be between 0 and 1. And what I want to argue is that like that's still kind of okay. Like you can make sense of that. So let me say, for example, I'll write out a mildly elaborate example. E1 is 0, 0.2, 0.3, 0. E2 is 1, 0.7, 0.2, 0. And E3, I'm just going to have 3. This has got to be 0. Now you can tell what they are because it's, I told you there's only going to be 3 of them. This would have to be 0.1. This would have to be 0.5. This would have to be 1. I say it would have to be because I'm assuming this condition that the vectors add up to all ones. And notice now that it's fully possible to have m, the number of events, be bigger than d. It wasn't in this case, but it's just because I wanted like something I could write on the board. And now, you know, if you're thinking like, wait, how are these events? Then, well, you can kind of think about it this way. Think about it like this. Like, imagine that like first you draw from P, and then if the outcome that you drew is 1. This is like outcome 1 here. So in this particular case, you would say, oh, event 2 happened. Now, if the outcome is 2 in your draw from P, that's like this column, then you say, OK, like event 1 happens with probability, what did I write, 0.2. And event 2 happens with probability 0.7. And event 3 happens with probability 0.1. Okay, and similarly, if you know if the draw from P is 3, then you say, oh, event 1 occurs with probability 30%, event 2 with probability 20%, event 3 with probability 50%. So like, you know, in order for this to like happen, you have like used additional randomness beyond just the randomness of P. But still, we have like a situation where we're able to define like mutually exclusive events where like one event always happens. Okay, it's just like not all the randomness comes from P. There's like P's randomness plus some additional randomness. Is that okay? So what I want you to, sorry, what's the question?
Yeah, question. Like, why do you have a bunch of events that are mutually exclusive?
Yeah, just because I want to have it. Just here's like a way that based on P, you can define mutually exclusive and completely exhaustive events. Yeah. Again, like, yeah, it doesn't seem super well motivated, but that's where you just got to like hang in there. But one thing I want you to notice is that, OK, what is the probability of event J? Well, you know, how can event J occur? Like, you have all the possible draws from P, I, and then if the I outcome occurs in P, then the event J happens with probability the jth coordinate of EI. And what I'm saying is this is just, again, the inner product of P and J. I got this messed up. Okay, so all I'm saying is, like, if you have a bunch of vectors, any number of vectors with these two properties, they're non-negative, they add up to the all ones vector, then you can somehow sensibly define these mutually exclusive events where the jth event happens with probability inner product of P and Ej. Okay? Okay, so that's a weird version of probability 101 definition number 2. And we'll do the quantum generalization now. Okay, so again, in the quantum generalization, you have like a source of randomness, quantum randomness rho, and you get like classical outcomes by measurements. So how do we know how to measure a state rho? Well, you can measure a rho in an orthonormal basis. That's like the most normal case. And there you'll have, if it's a d-dimensional state, you'll have exactly d different outcomes. And it's quite analogous to this case. There's also a way that's kind of analogous to the lumping, where you'll have fewer than d outcomes. And let me just explain this in words. This is kind of like if you have partial measurement. This is a bit of like a vague analogy, but like let's say it's a d-dimensional state because it's d is 2 to the power of q and you have q qubits. So you can measure the whole state, but as we've seen many times, if you have q qubits, you can measure just some of the qubits. And you'll get like, 2 to the r if you're measuring r qubits possible outcomes, which is less than d. Okay, and that's kind of like a lumping thing where you get like fewer things. You only sort of partially use up the randomness of your quantum source of randomness. Okay, so that's sort of analogous to this. And now I want to say sort of the most general thing you can do, which is analogous to this using additional randomness. And that's, okay, I'll call it additional randomness. So imagine you have like a bunch of, let's say, qubits. One thing you can do is you could add in like some new ancilla qubits. Just say, let's say initialized to 0, like you have some quantum state, you add in some more qubits. Now you have like a bigger system of dimension bigger than d. And like you could then maybe like do a big unitary. So not just like a d-dimensional unitary, but one on this like even bigger thing now. And now you could do a partial measurement or even a full measurement. And you could get thereby lots of different outcomes. In particular, if you did like a full measurement, you would actually get more than d outcomes. Right? So that's possible. You could use your randomness, your source of randomness rho, together with this is kind of like adding more randomness in to get more than d outcomes. That's possible. And so you can imagine even like think of this as like you should think of this as like a physical measuring device. Like you take a particle in state rho in, and this big device, it's a big old device, it like injects some like additional qubits in state 0 and does some quantum gates on them and has like maybe a big old physical measuring device at the end, and it spits out like even more than d possible classical readouts. Okay, that's something you could do. And now we're actually getting a little bit into like the axioms of quantum mechanics. This is actually like the most general thing that you can do. This is sort of the most general way of taking a quantum state and converting it into classical outcomes. And I'll think of the whole procedure. I'll call it a BODM. a big old device for measuring. Okay? Yeah, that's what it stands for. It's a big old like device that like takes in a quantum state and like reports an outcome. And also, it could have any number of outcomes. I'll say, call the outcomes or the readouts 1 through m. Okay. So, you know all the rules of quantum mechanics now. So you could think about like, okay, if I had a mixed state rho, which is a probability distribution over pure states, and I like put it into a quantum circuit that had some ancillas, and I did a full measurement, I could compute the probabilities with which I'd see each of the measurement outcomes, blah, 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 blah. Turns out, I'm going to skip the math, but it turns out there's like this big old device for measuring. You can boil it down into like some small mathematical objects, which will tell you the probabilities of all the outcomes. Okay, so just accept the following. This big old device for measuring, whatever it is, it yields m Hermitian matrices, E1 through EM. They're d by d. Okay, one for each outcome that satisfy two properties. Property 1 is that they're non-negative as matrices. They're positive. Remember, this is the positive semi-definiteness condition. And, well, you may guess it. E1 plus dot 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 plus EM is the identity matrix. And finally, so given your big old device for measuring, you can extract these matrices from it. And the probability that this thing, when applied to a state rho, reads out I is this rho matrix inner product with EI. So you can check actually that the most naive kind of measurement, where you have an orthonormal basis, U1 through UD, these E matrices are just, like UI, this projection onto the direction UI matrix. And we saw before, these are positive matrices that always add up to the identity. But in general, if you have any positive matrices that add up to the identity matrix, so this is kind of an if and only if. So if you have like any actual measuring device, you can get these matrices such that when you apply the measuring device to your state, it has these properties. And conversely, in principle, if you have any matrices that satisfy these properties, you can, in principle, build like a physical device, a physical like measuring instrument, which when applied to a quantum state, has this feature. Okay, so this is a little bit like a take my word for it statement, but that's the case. And like as a sanity check, this is sort of like I'll leave it as an exercise for you. First of all, condition 1 implies that all these numbers are positive, not negative. I mean, that better be the case if this is like a normal probability of something happening. This should be a non-negative number. But it's not hard to show that since rho is a positive matrix and EI is a positive matrix, this is non-negative. I think that will even be on your homework. This is for all I. And also, property 2 implies that the sum of these supposed probabilities is 1. Which indeed is consistent with like the statement that like, exactly one of these events always occurs. I mean, basically, you can already see, right? Put this sum into here, and it'll become the identity matrix in here. And you're doing the matrix inner product of rho with the identity matrix. It's like the sum of the diagonal entries of rho, which is 1. So yeah, this setup is the most general way physically of measuring a quantum state. And it's the quantum probability 101 definition of events. It's how you define events. Finally, I should tell you the real name of this big old device for measuring, BODM, is POVM. So you'll see this like a million times if you study quantum information theory. I don't even want to tell you what it stands for, some math thing. But for whatever reason, this collection of matrices satisfying these two properties is called the POVM. It stands for positive operator valued measure. But you should just think of it as like quantum events. Quantum version of like mutually exclusive and what is it? Completely exhaustive events. Any questions about this?
So does it still kind of, I don't know, maybe I just don't look at normal probability this way. Well, like when you define normal probability, you just have one event normally. Like you define one event. Why we don't do it in quantum?
We often do. Yeah, so a very common thing, if you're sort of very interested in like one event, is you'll have E. This is a good question. Which will be a a positive matrix whose eigenvalues are at most 1. And that'll be like the event that you care about. And then you'll like extend it to like a POVM by like taking the event and its complement. So given this, you'll like define E bar to be, this is a little linear algebra E, but the identity matrix minus E. And like this will imply that E bar is positive. By definition, they add up to 1. And then you can, the thing is you can build a measuring device that reports one of two outcomes, E or E bar. So like either event E happened or it didn't happen. So indeed, that is it's like a 2-outcome POVM is also an extremely commonly discussed thing. Especially if like you're building, if you think about like a quantum circuit whose goal is to solve a decision problem, can be thought of as a 2-outcome POVM. I mean, it's some complicated thing that takes, well, an input, and eventually it ends with a measurement. And you can set it up so that the measurement just has 2 outcomes, like yes or no. It's trying to decide a decision problem. And so it can be thought of as a 2-outcome POVM. Yeah, so the general, way this comes up typically is like, maybe you want to analyze or act upon some like quantum source of randomness, rho. And you'll sort of have the freedom to like design events, like as long as they satisfy these properties. You try to like design events, which are these matrices that like, such that these probabilities are like good for you somehow. That was like super vague, but I'll try to explain a little bit more about it later. It's like in quantum probability theory. Somebody might ask like, why events? Like, why do you define events? And you're like, well, we have like stuff that we want to analyze when you like roll a die. It's a little hard to explain without getting into examples, but we'll do that. Okay, one question you might have, I alluded to this earlier, but one question you might have is like, okay, this is a measurement, these POVMs. So if a POVM registers, outcome I, what does rho collapse to? It should collapse to something, right? This is a measurement. And the answer is, depends on how the POVM is implemented. So it's a bit of an unsatisfying answer, but like one way to say it is that you cannot tell just by knowing these matrices. It actually depends on the actual big old device for measuring that you built to implement this. You could build different devices that would come to the same E's, but would cause the state to collapse in different ways. And so basically, POVMs are only discussed in the world of quantum probability and quantum information theory when you don't plan on doing anything else with the state after you measure it. Like when the measurement, like in quantum computation usually, is like the end of the ball game. Like you really just care about what are the outcome probabilities of various things. You're not going to then continue to use the state. If you do care about that, then you have to again, you know all the rules. You have to just remember how it's built and like go back to the whole definition with pure states and so forth and so on and work it out. But this was something that like mystified me when I first learned it. That like okay, once you get this outcome, what does it collapse to? And you cannot tell just from the e's. But just very often you don't care. You'll see probably on the homework. Again, actually, for each way in which you build it, will yield actually some matrices mi such that ei is mi dagger mi. So for each way of building it, yields some matrices mi such that this holds. And then I can just tell you, since it's in my notes, when you register outcome I, it collapses to mi, let me get this right, mi rho mi dagger over the normalization condition, which is actually just rho ei. But somehow this doesn't come up that much. Okay, so that was events. And now finally, in probability 101, the next thing you do is random variables. And it's actually going to be a little bit easier than events, which is nice. Okay, so probability 101, definition 3, is about random variables. Okay, so given probability distribution P with D outcomes. Actually, you really have to remember the real true definition of random variables here. A random variable is it's just a real number for each outcome. That specifies a random variable. For each possible outcome, 1 through D, in your draw from P, you have an associated real number. That's the random variable's value on that outcome. And therefore, it's just any old vector, x. And what do you do with a random variable? There's pretty much only one thing you do in life with a random variable. You take its expectation. And so its expected value is maybe E sub P of x. It's the sum of the probability Pi of the ith outcome times the value of the random variable on that outcome, xi, which is just the inner product of P and x. Okay. So that's random variables in classical probability. So the quantum generalization of random variables has a nicer name. I mean, the generalization of events was called POVMs, which is sort of disgusting. But the generalization of a random variable is called an observable, which is pretty pleasant. And if you have a d outcome, a d-dimensional state. Well, remember I told you when you're generalizing from classical to quantum, just whenever you see vector, you replace it by symmetric, I should say, Hermitian matrix. So yeah, so an observable is literally just any old Hermitian matrix. X d by d. Okay, now we have to connect this to physical reality, which I will do in a second. Should also say, like in physics, like the observables are always things like position or momentum, or maybe somebody else chime in with one, spin or something. Energy. Yeah, it's some like physical property of a quantum state which can be measured and is real valued. So recall that any Hermitian matrix X, we love Hermitian matrices. They're so great because you can express them like this. Some I goes from 1 to d of some real number chi I, that's the eigenvalue, times, the projection operator in the direction of the ith eigenvector. So anyway, as we said, any Hermitian matrix looks like there's an orthonormal basis, and then it has the operation of scaling by the real amount chi I in the ith direction. So these are the eigenvalues. These are the orthonormal eigenvectors, ui's. This is a matrix. Okay, so how does this correspond to physical reality? Well, let's say you have a Hermitian matrix, an observable, X. Well, so it has this expression. Physically, you could build an instrument or a measuring device that did two things. I mean, first, it measures the state rho or the particle rho in the orthonormal basis of the u's, the eigenvectors of X. And I'll try to explain it more clearly. That's pretty good. Yeah. Well, if you have any questions. It just occurred to me, I could probably activate like half your cell phones by saying like, "Okay, Google." Oh, it didn't work. Loud enough. Okay, you can build an instrument that measures the state in this orthonormal basis, and then on outcome I between 1 and d, it reads out on its LCD readout the real number chi I. Okay, so you could build like a machine that has a hole in one side for like a d-dimensional particle to come in, and it has like an LCD screen on it. And when the particle comes in, it measures it in this basis, gets an outcome I, and then like if it gets 3, it prints whatever chi 3 is on its screen. And that's a machine or an instrument for measuring the X observable of the state. It could be like a position measurer, or I don't know, like a momentum measurer, what have you. Or, yeah. So, okay, now if you apply this instrument or measurer to rho, what would be the expected value of what you'd see on the readout screen? And here I'm using like expected value in like the classical probability sense of like, what's the expectation of that real number you see on the screen? Well, we can solve this using like the rules of classical probability. The answer to this question is, well, you sum over all the possible outcomes, I going from 1 to d, of, well, first of all, rho inner product with this matrix that projects onto ui, because this is the probability in the first step that your instrument reads out I. We've seen that a few times now. And then, if you do get that, you output the real number chi I. So this is the expectation of what you get on your classical readout. And now we'll just do some manipulations. We'll push this sum to inside here, and we'll also bring this scalar to inside here. And so we'll get, I should mention that this angle bracket thing, this inner product, is really linear. You can check that. Trace is a linear operator. It's the real inner product. So you get this, the inner product, the matrix inner product of rho with chi I ui, which is x. So given any Hermitian matrix X, if you build this measuring device, it's sensible in the sense that like the expected value of what you read out is this, the inner product of rho, the matrix inner product of rho with X. This is nice because it matches the little classical situation. And so to take it one step further, we just invent some additional new notation. We're just going to call this quantity, expected value sub rho of X. Okay? And it satisfies like all the properties of expected value that you love, like linearity of expectation and so forth. Okay. So again, like in classical probability, you can use this to your advantage. I mean, if you're trying to learn something or do something with rho, you can design your favorite Hermitian matrix to be an observable and have the property that you can understand something about the expected value of the readout. Let me just do one little calculation here that'll look a little bit unmotivated, but it'll just, on one hand, like give a little practice with thinking about this, and it'll also be like a little bit of a warm-up for a homework problem about the uncertainty principle. The uncertainty principle is really just about all this stuff, like things that look like the expectation of observables shows up in the statement of the uncertainty principle. So this is like a little slightly strange aside, but let's say you have some observable x. Let's look at the matrix x squared, which if you think about it linear algebraically, it's like the linear transformation of first doing x, then doing x again. And what does x do? Well, first of all, it has this basis, this orthonormal basis of u's, and it stretches the ith guy by chi I. So if you do that, and then you do that again, it has the effect of stretching the ith direction by chi I squared. Okay? So all of which is to say, this is Hermitian, and it's you can write it like this. Sum I goes from 1 to d of chi I squared times projection onto ui. Okay. You can also get that just by squaring this and doing some linear algebra. So you could build a physical device for measuring x squared. And what would its expected readout be? Well, it would exactly be, sorry, this is not what I wanted to say. Take it back. Imagine, forget this for a second. Imagine you had x, and you build the device for it. So you whenever you plug in a row, it reads out a real number. And we just decided that the expected value of that real number is, well, this thing. What if I asked you, what is the expected square of the readout? So let me write that. Expected readout for the x guy squared. Well, I would repeat this calculation, except I would put square here, right? That would be the expected value of the square of the readout for x. So I would get a square here. And then by this thing I told you on the top of the board, this thing with a square here is actually capital X squared. So I would get inner product of rho and capital X squared. And so this is expected value of capital X squared. I even confused myself here, but what I want to say is this is not tautological. We had to do a calculation to justify this. That the expected value of the square of the physical readout for the x measuring device is also given by that thing that you would really hope it was given by, namely the matrix inner product of rho and the square of matrix X. Okay, and that's really important, I guess, because then you can start defining, if this is really like probability 101 stuff, you can start to define things like the variance of X, which is expectation of X squared minus expectation of X squared. And like on one hand, it'll have a formula that involves like these quantities, but it'll also genuinely represent the variance of the real number readout of your X measuring device. So that like if you were going to use this X measuring device a bunch of times and you actually care statistically about the mean and variance of the readout on your machine, you could calculate it, using these formulas like inner product of rho and X squared minus inner product of rho and X squared. And again, I bring that up because, like, for example, it comes up in like these quantum statistics problems I'll say a few words about. And also, like, I mentioned Heisenberg's uncertainty principle. The general formulation of it, like, literally involves these quantities.
You can also write it like expectation of X minus expectation of X squared. Right?
You can write it. You can check that this variance is, again, like you would hope. It's also expectation or rho of X minus mu times the identity matrix squared, where mu is the real number expectation of X. And you have to even make sure that this is a Hermitian matrix, which it is. So yeah. Okay, so let me summarize. We spent the whole lecture doing math, but let me tell you a little bit about why. I'll do it over here. Okay, so let me just summarize first of all. This was kind of an intro to quantum probability theory. And why did we develop probability theory in real life? It was to model real world things involving chance, like flipping coins and rolling dice and sampling and polling and things like that. And we invent quantum probability to like encompass all that, and also the statistics of what happens when you like measure quantum particles with different kinds of measuring devices. And so we saw sources of randomness. These were our density matrices rho. And we saw the analog of events. That was these POVMs. And we saw the analog of random variables. That was observables. Great. Now, if you think about it back to classical probability 101, you define probability spaces and events and random variables. What else is there, right? That's it. You're done. That's, well, in some sense, all there is. So great. So we've set up all there is a little bit in quantum probability. Let me just actually make one little warning before of course, actually, there's more to it than that. And I'll say a few words about that as it ends. But let me just actually give one little warning here on the subject of random variables. One difference between this and classical probability is that if X and Y are observables, i.e. Hermitian matrices, well, of course, they're matrices. So X, Y is not necessarily the same thing as Y, X. And because of this, the mathematicians sometimes call this whole field non-commutative probability theory, because your random variables don't commute. So if you ever see that phrase, it's the same thing, basically. Yeah, X plus Y is Hermitian because X plus Y dagger is X dagger plus Y dagger, which if X and Y are Hermitian is X plus Y. Yeah. Yeah. Actually, in general, xy plus yx over 2 is always Hermitian, regardless whether this holds or not. So sometimes you can use this as like a substitute for the product xy. Okay, actually I kind of only brought that up to explain the name non-commutative probability theory. Okay, so I joked a little bit that once you define the source of probability in events and random variables, that's it, that's everything. But of course, there's much more to it than that. So I mean, in classical probability, once you define that, you can start talking about statistics, statistical concepts like standard deviation and variance and sampling and so forth. You can talk about information theory, like communication and entropy, and how much information you can get across a channel and stuff like that. You can talk about learning theory. I mean, you get samples from a distribution. You're trying to learn something about it. And there's quantum versions of all those things. The quantum statistics and quantum information theory, which we'll talk about next lecture a little bit. Quantum learning theory, and yeah, actually, I really like this area. This is actually the area of research that I'm working on in quantum. These problems like quantum learning theory, quantum hypothesis testing, quantum statistics, and information theory, Costin as well. And I really like it because first of all, it's different from quantum algorithms. It's the main thing you think of maybe when you think about quantum computation, quantum algorithms. But there's much more to it than that. All these fields like information theory, communication theory, learning theory, they all have a quantum analog thanks to just whenever you have something involving probability, upgrade it to quantum probability, and you have a whole new set of problems. And I also like it because it's more closely related to current reality. We're kind of far away from still building full-scale, million qubit quantum general-purpose computers. But on the other hand, we're not far away. We're currently doing experiments where you manipulate a few qubits, or you have some actual physical apparatus that produces qubits, or quantum states that are small dimensional, and you need to understand things like what state got produced. Can I learn what state was produced? If I run my apparatus a bunch of times, can I tell what quantum state it's outputting? Can I communicate that information over a quantum channel? So all these, questions that grow out of quantum probability theory are actually, I think, quite closely related to the things that are actually going on in experiments. Good. So next lecture, and maybe the next lecture after that, we'll talk about some quantum information theory. And so I'll see you on Thursday.